Everyone. In this video, we're going to go over section 4.1 problems. So first, let's determine if we have numbers being even or odd. And let's just recall the definition. So we have that a number is even, natural number is even if I can write it, or an integer really, if I can write it the way n equals to k, where k is an integer. Similarly, odd will be if I can write it on the form 2k plus 1, where k is another integer, but cases. So for example, 6 is an even number, and is because I can write it as 2 times 3. Minus 10 is going to be an even, and I can write it as twice times minus 5. 0 is also even because I can write it as 2 times 0. Now 101 is clearly going to be odd. I can write it as 2 times 50 plus 1. Okay? So now question number 2 is about if we have n as an integer, let's check if the following expressions are going to be even or odd. So we have 4n plus 3. So of course we want to write this in a way that is from the form 2k plus 1 or 2k. 4n plus 3, I can look at this and I can see it as 4n plus 2 plus 1. So it's looking like I'm going to be doing odd for this. Now I can factor 2 here, and if I factor 2, I get 2m plus 1 plus 1. And I can think of this as an integer. This is 2s plus 1. Notice that if n is an integer, then 2m plus 1 is also an integer. And so s, 2m plus 1 is also an integer. And then we're going to have that is odd. Let me just write here odd. Now for 6n clearly is something that we can see as twice times 3n, and I can very easily see this as twice l, where l is going to be 3n, and this clearly belongs to the integer. Since n is an integer, 3n is going to belong to the integer. So this is going to be an even quantity. 2n squared plus 3. Now, once again, I can separate this as 2n squared plus 2 plus 1. And now I can factor the 2, and I can see this as n squared plus 1 plus 1. And if I can consider, let's say that this is q n squared plus 1. Notice that if n is an integer, n squared is an integer, and n squared plus 1 is an integer. So q belongs to the integers, and this is 2q plus 1. So this quantity here is going to be odd. Okay? All right, moving on. We're going to have a list of positive divisor of each number, and let's check if it's prime or if it's composite. For 15, we clearly have that this is a composite number. We can see it as 3 times 5, so composite. And for now on, I'm just going to use C for composite, and I'm going to use P for prime. Divisors of 15, we have, of course, 1, we have 3, we have 5. We also have 15. So we have all these divisors. For 17, 17 is actually a prime number. So this is a prime, and the only divisors of this is 1 and 17. Now for 1, the only divisor is 1. And by definition, this is neither prime or composite. Okay? 24 is an even number, and I can see this barely 2 times 12. I can actually think of this as 2 to the 2 times 3. So if I do the full prime decomposition. And so this will be divisible by 2, or by 1, really, by 2, by 3, by 4, right? And then we can have combinations of also 2 and 3. And so we can have 6, but we can also have 8, right? We can also have 12, and of course 24. So all these are divisors of 24. There are multiple ways that you can represent this. You can also represent this as 6 by 4. So there's plenty of way that you can see that this is a composite number. Now let's go with some true and false questions. Every even integer is divisible by 2. So let's remember that is if it's even, if n that belongs to the integer is even, then S is k, so that n is equals to k. So just because it has this shape, 2k, we can say that we can see that it's divisible by 2. So this relationship n equals to k means that 2 divides n. Now, every odd integer can be written in the way 2k minus 1 for some integer k. This is also true. If you have that, let's say n that belongs to the integers can be written as 2s plus 1, right, initially. But then we can see this 1. You can see 1 as 2 minus 1, right? 2 minus 1 is 1. So now I can see this as 2 factor of x plus 1 minus 1. And so notice that x plus 1, since s is an integer, x plus 1 is also an integer. And let me call k equals x plus 1. So this will be seen as 2k minus 1 with k that belongs to the integers. So yeah, I can also rewrite any odd number in this way. Now we have the number 2 is the only even prime. This is true. This is certainly true. Any other prime is going to be divisible only by itself and by 1, and so there's no other possible even prime, because otherwise it will be divisible by 2. Now let's go with a couple proofs. So we have that the sum of an integer and an odd integer, even integer and odd integer, is odd. So this is a little bit of reviewing from what we saw in class. So let's say that you have 2 integers. So let n and s that belongs to the integer, and let's call n is going to be even and s is going to be odd. So notice that every time that we're doing proofs, we're breaking this into 5 steps. So this is going to be my assumptions. So now, as this is a step 1. A step 2 is going to be my definition of the assumptions. So if n is even, then n is equals to k for k that belongs to the integers. And if s is odd, then s is equals to l plus 1, where certain l that belongs to the integers. Notice that we cannot use the same letters. We need to use different letters. So now, what is this? The manipulation part, which is going to be step 3. Manipulation is going to be adding n plus s. And so n plus s is going to be 2k plus 2l plus 1. And now notice that I can pretty much factor this out, factor the 2, and I can see this as 2k plus l plus 1. Since both k and l are integers, then let's say I'm going to call this m is equals k plus l. This is also an integer, and so I can see that it has the shape 2m plus 1. This is the definition of the conclusion, which is my step 4. And my step 5 will be the conclusion. Step 5 will be the conclusion, which will be m plus s is odd. Okay, so the sum of an even integer and an odd integer is odd. All right, let's move to number 6. Number 6 is the product of two even integers is even. The proof here goes in the same way. So let's n and s be two integers, and let's say that n and s are even. And so this is step number 1, assumptions. I'm just going to use the a for now, so I don't have to write everything again. And so n equals to k and s equals to l, where k and l are integers. This will be my step 2, which is the definition of the assumptions. Now, step number 3 is the manipulation step, and I'm going to do n times s. So n times s is going to be 2k times 2l. So if I multiply this, I'm just going to get 4kl, but I can see this as twice 2kl. Now, let me call this, I'm just going to call j 2kl. Notice k is an integer, l is an integer, 2 is an integer. Multiplication of integers is integers, so this belongs to the integers. And that implies that n times s is 2j. And so this is my definition of the conclusion. And so my conclusion will be that n times s is even. So I'm completing the 5 steps of the proof. Now let's go to question number 7. If n is an odd integer, then n squared is odd. So let's do the same thing once again. Let's say n is something that belongs to the integers, and n is odd. This is a step 1. This is my assumptions. Step 2, my definition of the assumptions will be if n is odd, then it says k, so that n, k integer, so that n is 2k plus 1. And so now, number 3, my manipulation, I'm going to get the square of that number, and it will be the square of 2k plus 1 square. And this is 4k squared plus 4k plus 1. Now, I can rewrite this as twice 2k squared plus 2k plus 1. So notice that I'm kind of having the shape that I need for this. I'm going to call this L is equals 2k squared plus 2k. Notice k is an integer by definition, so 2k is going to be an integer. K squared is going to be an integer. And so 2k squared plus 2k is an integer. And now that we have this, then this can be seen as 2l plus 1 with L that is an integer. And so this is my definition of the conclusion as step number 4. And step number 5 will be n squared is odd, because I just proved that it has the odd definition. Now, last question number 8, we're going to prove that the product of any odd integers is going to be odd. So once again, let's assume that we have two integers, n and s, that belongs to the integers, and they're both odd. So this is step number 1, my assumptions. Step number 2 will be the definition of the assumptions, and I'm going to say n is 2l plus 1, and s is going to be 2m plus 1. So they're both odd. And this is for L, m, that belongs to the integers. Okay. So now let's do the product of them. So number 3, the manipulation step. It's going to be n times s. And n times s is going to be 2l plus 1 times 2m plus 1. So if I multiply this, I'm going to get 4lm, this by this, plus 2l plus 2m plus 1. So now I can factor a 2 out of this, and I'm going to get 2lm plus l plus m plus 1. And now, because l and m are integers, then I can say, well, let's call j equals 2lm plus l plus m. Notice that this is integer, this is integer, this is integer. So the entire thing, j, is going to be an integer, and this can be seen as the form 2j plus 1. And so this is our step number 4. This is the definition of the conclusion. We got that is an odd number. And so the conclusion, step number 5, is n times s is odd. Okay, so with this, we prove that the product of two integers that are odd is going to be odd as well. Let's continue with more exercises in part 2.